स्कूल में आपका दोबारा स्वागत है एंड आई एम डॉक्टर अंबिका फ्रॉम आचार्य नरेंद्र कॉलेज. टुडे वी विल डिस्कस बार पेंडुलम, damped oscillations and forced oscillation. In bar pendulum, we will discuss what is bar pendulum, what is the principle of bar pendulum, and how to calculate the acceleration due to gravity, the value of small g using bar pendulum. After that, we will discuss damped oscillation, what is damped oscillation, and what is the solution of the damped oscillations equation. And after that we will discuss forced oscillation, and after that we will discuss in forced oscillation we will discuss also resonance. So first we will discuss about the bar pendulum. In previous lecture we discussed about the simple pendulum and compound pendulum. So bar pendulum is also a example of compound pendulum. So what is the compound pendulum? In compound pendulum our mass is distributed. So, why is bar pendulum so called? Because a compound pendulum, like a swinging bar, has extended mass. It is referred to as a bar pendulum, and the simplest type of compound pendulum is a bar pendulum. It takes the shape of a rectangular bar with holes spaced evenly along its length. The bar pendulum is made up of a 1 meter long metallic bar. So, bar pendulum is the best example of a compound pendulum. When you want to know about the compound pendulum, so first you have to study bar pendulum, and after that you have to study Catus pendulum. So, when you have to calculate the value of small g, so first in lab you have to use bar pendulum, and after that you can use Catus pendulum, so that you know what is the difference between bar pendulum and Catus pendulum. So what is the principle of bar pendulum? So the bar is hung from a knife edge through one of the many holes along the length. It is free to oscillate about the knife edge as axis. Any displacement theta from the vertical position of equilibrium would give rise to an oscillatory motion, just as in the case of a simple pendulum. So this is the basic principle of bar pendulum. So now our aim is to find out the value of small g using bar pendulum when you are planning to perform experiment in your lab. So the aim of this experiment is to find the value of g. What is g here? G is the acceleration due to gravity, and basically its standard value is 9.8 meter per second square. So when you are performing a bar pendulum experiment in lab, obviously you need apparatus. So without that apparatus you are not able to measure the value of small g. So when we are planning to perform bar pendulum experiment, you need the rigid support, bar pendulum, meter scale, stopwatch and telescope. Okay, so rigid support, why we need rigid support? We need rigid support to support that bar pendulum. That means if you want to hang the bar pendulum, how will you hang? So you need to hang bar pendulum, so you need rigid support. Meter scale we need for the length measurement. If you want to measure any length, so for that you need meter scale. And telescope also, with the help of telescope you can just see the oscillations. And at last but not least, it's I think a main important apparatus which you are using for bar pendulum, that is the stopwatch. If you without a stopwatch you are not able to measure the time period. Okay, so stopwatch is a necessary here. So this is the main diagram of bar pendulum. So you can see this is a it's a straight meter rod like structure, and top point there are so many holes, and top holes, that is you can use you can say center of suspension. You can use that point for hanging also, and last one at bottom you can see that is the center of oscillation, and with the help at the last point you can just oscillate the bar pendulum. So this is the exact figure in lab. So you are able to see here, one is rigid body is there, and bar is also there. So top point, that is the center of suspension. With the help of that, you can just hang that bar in lab and center of oscillation. So what you have to do, in top portion you can say that is A side, and bottom side you can assume that is the B side. So this is also the bar pendulum, and the top point, that is the center of suspension, and mid point you can see that is the center of gravity, and last one, that is the center of oscillation. And L, small l, that is known, that is the from A side to center of gravity distance, and L dash, that is the center of gravity to last point distance, and total length, that is suppose that you are assuming that is capital L, and that is equal to small l plus L dash. In that diagram you can see that there are so many holes. Normally in experiment lab in bar we have 19 holes. So what will happen? 9, 9, 18. Okay, so A from mid hole is on 10th position. So from A to that mid position 9 holes, and bottom to that mid position 9 holes. So in center of gravity you can say that from when you are just adding from top, it is 10 number, and from bottom is also the 10 number. So that is the center of gravity. When you are performing bar pendulum experiment in your lab, first what you have to do, you have to choose the center point. So this is the setup. Now we are ready for to do experiment. So you can see that our bar is ready. We have stopwatch also. So what we have to do, we just hang our bar with that rigid body from top hole. Okay, top hole from A side. And now we can start to oscillate our bar. So suppose that we are planning to take for time for 20 oscillation. So you can start to oscillate that bar, and then for 20 oscillation you can note down the time with the help of that stopwatch. Now shift both the hinges. Now what you can do, you can just shift from both side, from B side, and note the time for the 20 oscillation. So now from the top and from the bottom, note the time for the 20 oscillation for both the sides. And after that, what you have to do, first what are you doing? You are doing from first hole you are hanging, and then note down the time period for the 20 oscillation. After that, shift the hinges till you reach next to the center of gravity. That means you have to note down the time for the 20 oscillation from A side, first hole, then second hole, then third, then fourth, and up to next to the center of gravity. And after that, what you have to do, you just reverse your bar, and same method repeat for the B side also. So we can say that we have to note down the time for the 20 oscillation from A side also, from B side also. So this is the table. So we have two sides, just we are assuming one side is A side and other side is the B side. So what we have to do, for A side you can see this is the table. We have to make this table also, and we are normally taking 9 reading. So here are 3 columns. First column, distance from center of gravity, that is we denoted here L, that will be in the centimeter. And second column, time, T for the 20 oscillation. So what we have to do, first what we were doing, first for 40 distance from the center of gravity, that means that first hole, the distance from the center of gravity, that first hole is 45 centimeter. So what we are doing for 20 oscillation, just note down the time. Similarly for 40 centimeter, then 35, then 30 centimeter, after that 25, 20, 15, 10 and 5. Okay, so you have to note down the time for the 20 oscillation. And you know very well, if we know the time for the oscillation, we can easily calculate the time period. So in third column, what you are doing, T equal to capital T, we are denoting time period by capital T, and capital T equal to small t by 20. So accordingly, just you can calculate all values and in third column. So you get all time period for 45, 40, 40, 30, 35, 25, 20, 15, 10 and 5 centimeter. So your A side experiment, A side observation is complete. Now same thing we have to do B side when our B side is up. So what you have to do again, distance from the center of gravity small l, that is also for the distances are 45, 40, 35, 30, 25, 20, 15, 10 and 5 centimeter. So again same thing you have to repeat, same method you have to repeat. So again note down the time for the 20 oscillation. You have to do oscillation, not to swing. Okay, so you have to calculate the time for the 20 oscillation. After that you can easily again calculate the time period for the one oscillation, that is small t by 20. So you have to complete these two tables, A side when A side is up and second one when your B side is up. So now your observation is complete. Now what we have to do, now we have to draw the graph. This is the graph. You can see we have to draw. So we have to draw all data points in our graph paper. So you can see at x-axis this is the distance from the center of gravity. Okay, distance from the center of gravity L, that will be in centimeter, and y-axis it's the time period, that is denoted by capital D. And you can see if the A side, when A side up you will get this type of graph, when B side up you will get this type of graph. So you have to draw graph freehand. Okay, you have to draw the graph freehand so that you will get this type of graph. So with the help of that graph, now what you have to do, you have to find out the L. L is the length of pendulum. How will calculate that L? Yeah, now we can do that. So in that graph you can see AB, okay, capital L equal to AC, L AC plus L dash CD, that is equal to AD, and capital L you can see here A, B, C, D and E. So L equal to capital L, that equal to BC plus CE plus BE. Okay, so the L is the length of pendulum. So what you have to do, take the mean of that mean L equal to AD. You know AD, you can measure. If you draw on graph paper, you can easily able to know the value of the AD and also the value of the VE. So if you know the value of AD and BE, you can easily calculate the value of L. So that L is the length of pendulum. Now we know the length of pendulum. We know the time period also. So what we can do now, we have now next is we have to calculate the value of small g. Small g is the acceleration due to gravity. Now put the values of, now we have this formula, small g equal to 4 pi square capital L upon t square, where capital L is the small l plus l dash, that is the length of the pendulum. Okay, capital L is nothing but is the simple the length of the pendulum. And what is capital T here? Capital T is the time period when the length of the pendulum is capital L. So what we have to do, g equal to 4 pi square L upon t, put the values of L here, capital L, and put the value of t. You have to square that, you have to do the square of the time period. So now from that formula you can easily calculate the value of small g, and the g is called acceleration due to gravity with the help of the bar pendulum. So if when you are performing this experiment in the lab, sometime you will get small g 10, the value of small g 10, sometime 9.7, sometime 9.3, because human error is there. So you know very well the value of small g equal to 9.8 meter per second square. So this is the standard value, and you got your calculated value. So you can just calculate the percentage error, so that you are able to say, yeah, I am getting this the 3% of error, 4% of error. So percentage of error you can calculate. And we know that Earth is not ideally sphere. Basically, Earth is not ideally sphere. It is pear shape. It is pear shape. So its radius, normally what will happen? Its radius is more at the equator and short at the poles. So we can say the value of small g, that is lesser at equator and more at poles. And we know we have small g, that is the acceleration due to gravity, but we have capital G also. Okay, so small g is the acceleration due to gravity, and it is a variable dependent on the mass and radius of the planet. So we have a relation between small g as well as capital G. Small g equal to capital G m upon r square. Capital G, what is capital G here? Capital G is a universal constant, and it is the gravitational constant, and its value is 6.67259 into 10 to the power minus 11. So it's very important relation. So this is the relation between the small g and capital G. Now we'll talk about the damped oscillation. We know the simple harmonic motion, simple harmonic oscillation, and now we'll talk about the damped oscillation. So what is damping? Okay, in damped oscillation, what is damping? So what will happen in damped oscillation? Our amplitude is decreasing with time. That's why we can say damping is going on. So where the force is proportional to the speed of the moving object and acts in the direction opposite the motion. The retarding force can be expressed as capital R equal to minus BV, where that, what is that, small b? Small b is a constant. We can call that constant damping coefficient. Okay, that small b is called the damping coefficient. And we have restoring force also. So what is the value of the restoring force? We already know the value of restoring force is minus kx, where k is force constant and kx is the displacement. So we know, then we can write Newton's second law. We know Newton's second law, F equal to ma. So here what we are doing, summation of fx equal to minus kx, restoring force, minus bbx. What is bbx? That is the retarding force. So we are writing that Newton's law in terms of that. So summation of fx equal to minus kx minus bvx equal to ma, where a is the acceleration, v is the velocity. So we know very well, if we know the value of the displacement x, suppose x is the displacement, so we can calculate the velocity as well as acceleration. So if x is given, so how we'll calculate the velocity? Velocity we can calculate, just differentiate that displacement. So v equal to dx by dt. Okay, and again if we want to calculate the accelerate, so what we have to do? We have to again double differentiate the displacement. Yeah, we can say that we can just differentiate that velocity. So v equal to dx by dt. And if you want to calculate the acceleration, just we can again differentiate velocity, that is dv by dt. So dv, if you will explain that, so what will happen? Its value will be a equal to d square x by dt. So what we are doing here, we are just put the value of velocity in terms of the displacement and the value of acceleration in terms of displacement. So we will get this equation, minus kx minus b dx by dt equal to m d square x by dt, where dx by dt is the velocity and d square x by dt square, that is the acceleration. So when the retarding force is small compared with the mass restoring force, so what will happen? That suppose that b is small, so the solution will come x t equal to a e raised to power minus b upon 2m t cos omega t plus phi. So this is the solution of that equation. Now omega, what is the omega? We know very well it's angular frequency. So omega equal to root k by m minus b upon 2m whole ka square. But we know the value of omega not equal to root k by m, and omega not equal to root k by m, that is called the natural frequency of the undamped oscillators. Okay, when b is 0. So we will get natural frequency where damping will not be there. Damping will not be there means b equal to 0. So in that case we will get the natural frequency. So the last two equations show that the driving force and the amplitude of the oscillator which is constant for a given driving force. So what will happen when we are talking about the small damping? Okay, when we are talking about the small damping. So for small damping, the amplitude is large. Okay, for small damping, what will happen? Amplitude is always large. And when the frequency of the driving force is near the natural frequency of oscillation, so what will happen in this case? Suppose that omega is approximately equal to omega naught, where omega naught is the frequency, and this is called the resonance, and the natural frequency is called the resonant frequency. So we can say that what is the condition for the resonance? So we can say that the condition for best condition for resonance is omega is approximately equal to omega naught. So this is the condition for the resonance. You can see what is that. This is a diagram, and it is clear from that diagram how damping is going on. You can see that at x-axis here time and y-axis its amplitude, and you can see that capital A at top of the y-axis. That capital A is the initial amplitude, and that dotted line, the envelope of the amplitude decays exponentially. Okay, that dotted line shows that our amplitude decays exponentially. That means with time our amplitude going to decrease. So in that condition, x max equal to a e raised to power minus b t upon 2m. So from that diagram you can see that how damping is going on. Now we have three types of damping: underdamped oscillators, critical damped oscillator, and overdamped oscillator. Okay, so in graph you can see at x-axis this is T. There are three pattern: blue one, red one, and black one. Okay, here we are denoting A, B, and C. So what will happen in underdamped oscillator? R max that is equal to B V max, that is less than K of A. If we will get this condition, so we can say that system oscillate with a damping amplitude. So that blue one, you can say that is the underdamped oscillation. Second one, B, we are denoting that graph by B, that is the critically damped oscillator. So when we will get the critical damped oscillators? We will get critical damped oscillator when small b has critical value Bc that equal to 2m omega naught. So we can say that in that condition system does not oscillate. Our system is not going to oscillate, just return to the equilibrium position. That C1 you can see that C graph is the condition for the overdamped oscillator. So in that overdamped oscillator, what will happen? R max equal to V max, that is greater than Ka, and B upon 2m is greater than omega naught. System does not oscillate, just return to the equilibrium position. So there are basically three types of damping: underdamped, critical damped, and overdamped. Now we'll talk about driven harmonic oscillation. A driven or force oscillator is a damped oscillator under the influence of an external periodic force Ft equal to F naught sine omega t. So the second Newton's law of the force oscillator is F naught sine omega t minus B dx by dt minus kx equal to md square x upon dt square, and the solution of that equation is x equal to a cos omega t plus phi, where and a equal to f naught m upon omega square minus omega naught square whole square plus b omega upon m whole square. So the force oscillator vibrates at the frequency of the driving force, and the amplitude of the oscillator is constant for a given driving force. For small damping, the amplitude is large when the frequency of the driving force near the natural frequency of oscillator, and the dramatic increase in amplitude near the natural frequency is called resonance, and the natural frequency omega naught is also called the resonant frequency of the system. This is the simple harmonic motion pattern, and you can see though that motion continues indefinitely, only conservative force acts, so that in simple harmonic motion we can say that mechanical energy is constant. It is clear from that pattern. What about in the damped oscillator? Dissipative forces remove energy from the oscillator, and that's why the amplitude decreases with time. Now we'll talk about free and forced oscillation. What happened in free oscillation? The system oscillates without any force applied, and its frequency is its natural frequency, and there is little, or we can say that no damping. In what happened in the forced oscillation? The system responds to a regular periodic driving force. So we can say that like continuously pushing a child on a swing. So if the frequency of the applied force equal to the natural frequency of the system, so we can say that resonance occurs, and this is when the system oscillates with maximum amplitude. If you push the child on the swing, each time they reach maximum amplitude, their oscillation amplitude increases, and if you push when they are halfway back toward you, their oscillation amplitude decreases. So this is the graph of the resonance, and from that diagram it is clear when your frequency is maximum, you can say that is a resonance frequency. So when the natural frequency equal to the driving frequency, then this is at the maximum and is said to be a resonance. Now we will tell about what is the difference between free oscillations and forced oscillation. So in free oscillations, in which a body of system oscillates with its own natural frequency without being acted upon by an external force. But what will happen in the forced oscillation? In forced oscillation are the oscillation in which the body oscillates with the frequency other than its natural frequency under the influence of an external force. In free oscillations, they occur due to elastic force and inertia of the system. In forced oscillation, they occur due to action of periodic force applied externally. But in free oscillation, diminishes gradually due to the resisting force called the damping force, and in forced oscillation, persists as long as the body acted upon by the external force. In free oscillations, the frequency depends on the mass and elasticity of the body. The frequency is equal the frequency is equal to the frequency of periodic force applied to force in forced oscillation. The best example of free oscillations, when you push a swing just once, it oscillates its natural frequency, so it acts as a free oscillation. And the example of forced oscillation is that if you push the swing each time it slow down, it will continue to swing because external force is applied to it, so it becomes a forced oscillation. So this is the best example of forced oscillation and free oscillations. Thank you so much.